The universe, in the most fundamental sense, presents itself to observation as the totality of space, time, matter, and energy. A system whose boundaries remain undefined and perhaps undefinable, whose age has been measured with increasing precision over the past century, and whose contents continue to reveal properties that challenge the explanatory frameworks developed to account for them. The current estimate for the age of the observable universe stands at approximately 13.8 billion years, a figure derived from measurements of the cosmic microwave background radiation, from calculations of the expansion rate of space, and from the observed ages of the oldest stellar populations, all of which converge with remarkable consistency despite being based on independent methods and assumptions. This convergence itself represents a significant development in the history of cosmology, a field that through much of the 20th century remained characterized by competing models and fundamental uncertainties about even the most basic parameters of cosmic structure. The observable universe, distinguished carefully from the universe as a whole, refers specifically to that portion of cosmic space from which light has had sufficient time to reach Earth since the beginning of cosmic expansion, a sphere with Earth at its centre, not because Earth occupies any privileged position, but simply because the definition refers to observability from this particular location. The radius of this observable sphere measures approximately 46.5 billion light-years, a value that exceeds what might naively be expected from multiplying the age of the universe by the speed of light, and this discrepancy requires explanation in terms of the expansion of space itself, which has carried distant regions progressively farther away, even as light from those regions travelled toward us. The most distant objects currently observable emitted their light when they were much closer to our present location, but the expansion occurring during the billions of years of that light's journey has stretched the intervening space so that the sources now lie at distances far greater than the light travel time alone would suggest. Within this observable volume, current estimates place the number of galaxies at approximately 200 billion to 2 trillion, a range that reflects ongoing refinements in observational techniques and theoretical corrections for galaxies too faint or too distant to be directly detected. Each of these galaxies contains on average somewhere between 100 million and 1 trillion stars, though the distribution is highly skewed, with numerous small dwarf galaxies containing relatively few stars, and a smaller number of giant elliptical galaxies containing stellar populations numbering in the trillions. The total number of stars in the observable universe thus falls somewhere in the range of 10 to the power of 22 to 10 to the power of 24, numbers so large that they resist intuitive comprehension, yet remain finite and in principle countable, representing discrete physical objects each with its own history of formation, evolution, and eventual death. The composition of the universe, as currently understood, presents one of the more striking features revealed by 20th and 21st century cosmology, namely that the visible matter constituting stars, planets, gas clouds, and all other directly observable objects represents only a small fraction of the total mass-energy content. Ordinary baryonic matter, meaning matter composed of protons, neutrons, and electrons in the configurations familiar from chemistry and everyday experience, accounts for approximately 5% of the cosmic total. An additional 27% consists of what has been termed dark matter, a substance whose existence is inferred from its gravitational effects on visible matter, on the bending of light passing near galaxies and galaxy clusters, and on the cosmic microwave background radiation, but which does not interact with electromagnetic radiation and therefore cannot be observed directly through any telescope sensitive to light. The remaining 68% of the mass-energy content takes the form of dark energy, a component even more mysterious than dark matter, whose primary observable effect is the acceleration of cosmic expansion, a phenomenon discovered in 1998 through observations of distant supernovae and confirmed subsequently through multiple independent lines of evidence. This inventory of cosmic contents would have been unrecognizable to astronomers working as recently as a century ago, when the very existence of galaxies beyond our own remained uncertain and the scale of the universe was drastically underestimated. The term island universes had been proposed in the 18th century to describe the faint nebulous patches visible through telescopes, but whether these represented distant systems comparable to our own Milky Way or merely gas clouds within, it remained contentious until Edwin Hubble's observations in the 1920s established conclusive distance measurements to several nearby galaxies, demonstrating that they lay far outside the boundaries of the Milky Way and fundamentally revising the conception of cosmic scale. Hubble's subsequent discovery of a relationship between the distances to galaxies and the speeds at which they appeared to be receding, now known as Hubble's law, provided the first observational evidence for the expansion of the universe, a theoretical possibility that had been derived from Einstein's general relativity by Alexander Friedmann and Georges Lemaitre, but which lacked empirical confirmation until these spectroscopic measurements revealed the systematic redshifting of galactic light, the expansion of space itself, as opposed to the motion of objects through space, represents a conceptual distinction of considerable importance for understanding cosmological processes. Objects within gravitationally bound systems such as galaxies, galaxy clusters, or even the local group of galaxies do not participate in cosmic expansion, their internal gravitational attraction being sufficient to overcome the expansive tendency. The Andromeda Galaxy, for example, approaches the Milky Way at approximately 110 km per second, rather than receding from it, because the gravitational binding between these two large spiral galaxies and their smaller companions exceeds the expansive force at this relatively close separation of 2.5 million light-years. On larger scales, however, where gravitational binding becomes insufficient, the expansion dominates, and the distances between unbound systems increase progressively over time. This expansion does not occur at a single uniform rate throughout cosmic history, having decelerated during the earlier epochs when matter density was higher and gravitational attraction more effective, and then accelerating in more recent cosmic time as dark energy has come to dominate the mass energy content. The cosmic microwave background radiation, detected accidentally in 1965 by Arno Penzias and Robert Wilson, and subsequently studied in extraordinary detail by satellite missions including COBE, WMAP and Planck, provides a snapshot of the universe as it existed approximately 380,000 years after the initial expansion began. At this epoch, the temperature of the universe had declined sufficiently for electrons and protons to combine into neutral hydrogen atoms, an event termed recombination, despite the fact that electrons and protons had never previously been combined at the temperatures prevailing in earlier cosmic history. This transition from ionized plasma to neutral gas rendered the universe transparent to electromagnetic radiation, allowing photons to travel freely without being scattered by charged particles, and these photons have continued travelling through expanding space for the subsequent 13.8 billion years, their wavelength stretched by a factor of approximately 1100 from the visible spectrum to the microwave region. Their temperature cooled from several thousand degrees to 2.725 degrees above absolute zero. The precise measurement of this radiation, including both its average temperature and its minor fluctuations from point to point across the sky, has provided the most detailed constraints available on cosmological parameters, including the geometry of space, the age of the universe, the relative proportions of different matter and energy components, and the statistical properties of the density fluctuations that eventually grew into the large-scale structure of galaxies and galaxy clusters. The fluctuations in the cosmic microwave background represent density variations of only about 1 part in 100,000, seemingly negligible inhomogeneities that nonetheless provided the seeds from which all subsequent cosmic structure developed through gravitational amplification over billions of years. Regions of slightly higher density exerted slightly stronger gravitational attraction on surrounding matter, drawing in additional mass, increasing their density further, and attracting still more matter in a process of progressive concentration that eventually produced the galaxies, galaxy clusters, and filamentary structures observed in the present universe. This growth of structure from primordial fluctuations depends sensitively on the properties of dark matter, which does not interact electromagnetically, and therefore could begin collapsing into dense regions earlier than ordinary baryonic matter, which remained coupled to the photon field until recombination. The presence of dark matter thus acted as a scaffolding on which baryonic matter could subsequently accumulate, falling into the gravitational potential wells already established by dark matter concentrations and eventually forming the luminous galaxies visible through telescopes. Without dark matter, according to current theoretical understanding, the density fluctuations present in the early universe would have been insufficient to produce the observed structure within the available time, and the universe would appear substantially different from what observations reveal. The nature of dark matter remains among the most significant open questions in contemporary physics and cosmology, with proposed explanations ranging from as-yet undiscovered elementary particles to modifications of gravitational theory at large scales. The particle physics candidates include various theoretical entities collectively termed WIMPs, for weakly interacting massive particles, which would have been produced in the early universe and would have survived until the present day due to their lack of strong or electromagnetic interactions. Extensive experimental searches for direct detection of dark matter particles, using deeply buried detectors designed to register the rare collisions of passing dark matter particles with atomic nuclei, have thus far yielded no confirmed positive results, placing increasingly stringent constraints on the properties such particles could possess. Indirect detection strategies searching for the products of dark matter, particle annihilations in regions of high dark matter density, have similarly failed to produce unambiguous evidence, though some anomalous signals observed by satellite experiments continue to generate discussion. Collider experiments at facilities such as the Large Hadron Collider have sought evidence for the production of dark matter particles in high-energy collisions, again without success to date, and the parameter space available for the simplest theoretical models continues to shrink under these combined experimental pressures. Alternative explanations invoking modifications to gravitational theory, rather than unseen matter, have been developed. Most notably modified Newtonian dynamics, or MOND, which proposes that gravitational attraction deviates from the Newtonian prediction at very low accelerations characteristic of galactic outskirts. This approach successfully accounts for the rotation curves of spiral galaxies without requiring dark matter, but encounters difficulties when applied to larger structures such as galaxy clusters, or to the acoustic oscillations visible in the cosmic microwave background, phenomena that standard dark matter models explain with considerable precision. The tension between the empirical successes of MOND at galactic scales and its inadequacies at larger scales has motivated various relativistic extensions and hybrid approaches, but no fully satisfactory alternative to the dark matter hypothesis has emerged that matches its explanatory scope across the full range of relevant observations. Dark energy presents even more profound theoretical challenges than dark matter, because while dark matter can plausibly be identified with some species of elementary particle, dark energy appears to require either a cosmological constant representing the energy density of empty space itself, or some form of dynamical field evolving over cosmic history, or some modification of general relativity at cosmological scales. The cosmological constant interpretation, mathematically the simplest option, identifies dark energy with the vacuum energy predicted by quantum field theory to arise from quantum fluctuations of all particle fields even in empty space. This identification confronts the infamous cosmological constant problem, namely that naive estimates of vacuum energy based on quantum field theory exceed the observed dark energy density by some 120 orders of magnitude, a discrepancy so vast that it cannot be attributed to calculational uncertainties and must reflect some fundamental gap in theoretical understanding. Various proposed resolutions invoke supersymmetry, anthropic selection in a multiverse, or novel physical principles, but none has gained consensus acceptance, and the problem remains open. The observational evidence that dark energy density has remained approximately constant over the past several billion years favours the cosmological constant interpretation over dynamical field models that would predict evolution, but the precision of current measurements leaves room for departures from constancy that future observations may detect or further constrain. The formation of the first stars in the early universe occurred several 100 million years after the initial expansion, during an epoch termed the Cosmic Dark Ages because no luminous sources yet existed to produce detectable light. The first stars formed from clouds of primordial hydrogen and helium gas, these being the only elements produced in significant quantities during the first few minutes of cosmic history when temperatures and densities briefly reached values sufficient for nuclear fusion. These first-generation stars, termed population 3 stars, to distinguish them from later stellar populations enriched with heavier elements, are thought to have been substantially more massive than typical present-day stars, with masses reaching hundreds of times that of the Sun. The absence of heavier elements in the primordial gas inhibited the radiative cooling processes that allow present-day gas clouds to fragment into smaller pieces, resulting in larger characteristic masses for the collapsing fragments and consequently for the stars they formed. These massive first-generation stars burned through their nuclear fuel rapidly, with lifetimes of only a few million years, ending their lives in catastrophic explosions that dispersed the heavier elements synthesized in their interiors into the surrounding gas. No population 3 stars have been conclusively identified through observation, consistent with the expectation that all such stars would have exhausted their fuel and died long ago given their short lifetimes, though searches continue for their signatures in the most distant observable regions and in the chemical compositions of the oldest surviving stars which may retain traces of enrichment from population 3 supernovae. The nucleosynthesis of elements heavier than lithium takes place almost entirely in stellar interiors and in stellar explosions, a process sometimes described as "we are made of star stuff," though this phrasing, while evocative, somewhat oversimplifies the chain of events involved. The fusion of hydrogen to helium occurs in the cores of main sequence stars like the Sun, proceeding through either the proton-proton chain or the CNO cycle depending on stellar mass and central temperature. Helium fusion to carbon occurs in more evolved stars after the exhaustion of hydrogen in the core, and successive burning stages in massive stars produce oxygen, neon, magnesium, silicon, and eventually iron group elements at the center. Elements heavier than iron cannot be produced through fusion in stellar cores because the fusion of iron group nuclei consumes rather than releases energy, and the production of these heavier elements requires either slow neutron capture in asymptotic giant branch stars, producing roughly half of the elements beyond iron over timescales of thousands of years, or rapid neutron capture in explosive environments such as core collapse supernova and neutron star mergers, producing the other half in a matter of seconds. The relative abundances of elements observed in the solar system and in stellar spectra throughout the galaxy reflect the integrated contributions of these various nucleosynthetic processes over billions of years, with characteristic signatures allowing identification of which processes dominated for particular elements. Neutron star mergers, confirmed observationally through the detection of gravitational waves combined with the electromagnetic observations in 2017, have been demonstrated to produce substantial quantities of heavy R-process elements, including gold and platinum, thereby resolving a long-standing debate about the astrophysical sites responsible for these elements. The event designated GW170817, detected by the LIGO and Virgo gravitational wave observatories, and subsequently observed across the electromagnetic spectrum from gamma rays to radio waves, produced spectroscopic evidence for the synthesis of elements with masses extending beyond uranium, with the total mass of heavy elements ejected estimated at several hundredths of a solar mass. The characteristic glow of this material, powered by the radioactive decay of newly synthesized heavy nuclei, matched theoretical predictions for the kilonova phenomenon that would accompany neutron star mergers, providing direct evidence for this nucleosynthetic site. The frequency of neutron star mergers in the galaxy appears consistent with these events being a major, or perhaps dominant source of our process elements, though contributions from rare types of supernova cannot be excluded, and the relative importance of different sources may have varied over cosmic history. The formation of the solar system approximately 4.6 billion years ago exemplifies the processes by which stars and their accompanying planetary systems arise from interstellar gas clouds, though important questions remain about the specific mechanisms and sequences of events involved. The collapse of the pre-solar nebula, likely triggered by the shockwave from a nearby supernova, as evidenced by short-lived radioactive isotopes whose decay products persist in primitive meteorites, produced a rotating disk of gas and dust surrounding the forming sun. Within this disk, solid particles condensed from the cooling gas aggregated through collisions into progressively larger bodies termed planetesimals, and eventually accumulated into the planets, moons, asteroids, and comets of the present system. The inner regions of the disk, being hotter, retained only refractory materials with high condensation temperatures, resulting in the rocky terrestrial planets Mercury, Venus, Earth, and Mars, while the cooler outer regions allowed volatile materials including water ice, ammonia, and methane to condense, contributing to the massive cores that captured thick atmospheres of hydrogen and helium to form the giant planets Jupiter, Saturn, Uranus, and Neptune. The arrangement of planets in the solar system does not simply reflect their formation positions. A substantial orbital migration occurred during the early history of the system. The Nice model, named for the French city where it was developed, proposes that the giant planets formed in a more compact configuration than their present orbits, and subsequently migrated to their current positions through gravitational interactions with a disk of planetesimals beyond Neptune. This migration produced a period of dynamical instability approximately 3.9 billion years ago, during which the orbits of the giant planets shifted significantly, scattering the planetesimal disk and producing the late heavy bombardment recorded in the heavily cratered surfaces of the Moon, Mercury, and other bodies. Evidence for this bombardment appears in the dating of lunar impact basins and in the ages of impact melt samples returned by Apollo missions, though the exact timing and duration of the bombardment period remain subjects of ongoing investigation. The migration of Jupiter and Saturn may also have influenced the inner solar system, with some models suggesting that Jupiter first migrated inward toward the Sun before reversing course and moving outward, a scenario termed the Grand Tack that could explain various features of the terrestrial planet zone, including the small mass of Mars and the compositional structure of the asteroid belt. Earth's moon, the fifth largest satellite in the solar system, formed through a process that current understanding attributes to a giant impact between the early Earth and a Mars-sized body conventionally named Theia, occurring approximately 4.5 billion years ago, shortly after Earth's primary accretion. This hypothesis accounts for several distinctive features of the Earth-Moon system, including the angular momentum of the system, the Moon's relatively small iron core compared to its overall size, and the geochemical similarities between lunar and terrestrial materials. The impact would have vaporized substantial portions of both bodies, producing an orbiting disk of debris from which the Moon subsequently accreted over a relatively short timescale of perhaps months to years. The energy released by the impact would have rendered Earth's surface molten, forming a magma ocean that took millions of years to solidify, and whose crystallization history remains recorded in the oldest terrestrial and lunar minerals. The origin of water on Earth, long attributed primarily to cometary delivery, increasingly appears to involve contributions from carbonaceous asteroids, and possibly from the primordial nebula gas, with the giant impact potentially having caused substantial loss of any early atmosphere and surface water, complicating reconstruction of the early hydrological history. The development of Earth's atmosphere and oceans involved a complex interplay between volcanic outgassing, cometary and asteroidal delivery, atmospheric escape, and chemical reactions with the surface, producing conditions that eventually permitted the origin and evolution of life. The earliest atmosphere, immediately following the formation of the Moon, likely consisted primarily of silicate vapor from the cooling magma ocean, transitioning as temperatures declined to a steam atmosphere that eventually condensed into liquid oceans once surface temperatures fell below the critical point of water. Volcanic outgassing continued to release carbon dioxide, nitrogen, water vapor, and other volatiles into the atmosphere, while the gradual escape of hydrogen to space slowly altered the oxidation state of the surface and atmosphere for hundreds of millions of years. The Great Oxidation Event approximately 2.4 billion years ago marks a dramatic transition in atmospheric composition, as oxygen produced by cyanobacterial photosynthesis accumulated to levels sufficient to leave clear signatures in the geological record, including the cessation of formation of detrital uraninite and pyrite, the disappearance of mass-independent sulfur isotope fractionation, and the appearance of continental red beds indicating oxidative weathering. This rise of oxygen proceeded in stages rather than continuously, with evidence for oxygen fluctuations and possibly one or more returns to more reducing conditions before the permanent establishment of an oxidizing atmosphere. The origin of life on Earth remains one of the most significant unsolved problems in natural science, with multiple competing hypotheses addressing different aspects of the transition from prebiotic chemistry to the first living systems. The timing of life's origin is constrained by several lines of evidence, with the oldest potential signs of life appearing in rocks dated to approximately 3.5 to 3.8 billion years ago, including stromatolites in Australian and South African formations isotopically like carbon in Greenland rocks interpreted as biological fractionation, and possible microfossils whose interpretation remains contested. The late heavy bombardment, if it occurred as hypothesized around 3.9 billion years ago, would have posed severe challenges to any life existing at that time, potentially sterilizing the surface through the energy of large impacts, though deep subsurface environments might have provided refugia. The relatively short interval between the end of heavy bombardment and the earliest evidence for life suggests either that life arose rapidly once conditions permitted, that life originated before the bombardment in protected environments and survived through it, or that life was delivered to Earth from elsewhere in the solar system through a process termed panspermia, though this hypothesis postpones rather than resolves the question of life's ultimate origin. The chemical and physical conditions under which life might have originated have been the subject of extensive experimental investigation since the Miller-Urey experiment of 1953 demonstrated the synthesis of amino acids from simple gases under simulated early Earth conditions. Subsequent work has identified numerous potential settings for prebiotic chemistry, including hydrothermal vents on the ocean floor, volcanic hot springs on land, tidal pools subject to wet-dry cycles, and even ice formations that concentrate reactants through freeze exclusion. The RNA world hypothesis proposes that early life relied on RNA molecules that served both as genetic material and as catalysts, with DNA and proteins arising later as refinements of this original system, and laboratory experiments have demonstrated that RNA molecules can catalyze a variety of reactions, including their own replication under certain conditions. Alternative hypotheses emphasize the importance of metabolism-first scenarios in which self-sustaining chemical reaction networks preceded the development of genetic polymers, or the role of mineral surfaces in catalyzing and organizing prebiotic reactions. The problem of homochirality, namely why biological molecules use exclusively left-handed amino acids and right-handed sugars rather than racemic mixtures, remains unexplained, with proposed solutions including chance selection, amplified by autocatalytic processes, asymmetric synthesis induced by circularly polarized light, or processing on the surfaces of chiral minerals. The evolution of life from its origin through to the present day has produced an estimated 8 million currently living species, though this estimate carries substantial uncertainty, with some calculations suggesting the total might exceed 10 million, and has generated over the course of Earth's history a vastly larger number of species that have since become extinct, with estimates suggesting that over 99% of all species that ever lived no longer exist. The tree of life, representing the genealogical relationships among all organisms, has been reconstructed through comparative analysis of morphological features, molecular sequences, and more recently complete genome sequences, revealing that all known life shares common ancestry and can be divided into three fundamental domains: bacteria, archaea, and eukarya. The separation between bacteria and archaea, once thought to represent the deepest division in the tree of life, has been complicated by discoveries suggesting that eukarya may have arisen from within archaea through a process involving the symbiotic incorporation of bacterial cells that eventually became the mitochondria essential to eukaryotic energy metabolism. This endosymbiotic origin of mitochondria, and the separate endosymbiotic origin of chloroplasts in photosynthetic eukaryotes, represents a distinctive evolutionary mechanism in which entire organisms become integrated as components of more complex cells, a process whose importance in evolutionary history has gained increasing recognition. The Cambrian explosion, occurring approximately 540 million years ago, marks an episode of apparently rapid diversification, during which most of the major animal phyla first appear in the fossil record, including groups as disparate as arthropods, mollusks, echinoderms, and chordates. The causes of this dramatic increase in morphological disparity remain debated, with proposed explanations including rising atmospheric oxygen levels, enabling larger body sizes and more active metabolisms, the evolution of predation triggering an evolutionary arms race in defensive and locomotory adaptations, changes in ocean chemistry related to continental weathering, the evolution of developmental genetic toolkits enabling new body plan variations, or simply the acquisition of hard mineralized skeletons that dramatically improve preservation potential, revealing diversity that had previously existed but left no fossil trace. The Ediacaran biota that preceded the Cambrian fauna, known from fossil assemblages dating to approximately 575 to 539 million years ago, included large soft-bodied organisms whose relationship to later animal groups remains unclear, with some apparently representing extinct body plans without modern descendants. The transition from Ediacaran to Cambrian ecosystems involved not merely the addition of new groups, but the replacement of an earlier ecological order, with the causes of Ediacaran extinction possibly related to the ecological changes accompanying the Cambrian radiation itself. The history of life has been punctuated by mass extinction events in which substantial fractions of existing species disappeared in geologically brief intervals, with the recognised Big Five mass extinctions occurring at the end of the Ordovician, in the late Devonian, at the end of the Permian, at the end of the Triassic, and at the end of the Cretaceous. The end Permian extinction, approximately 252 million years ago, was the most severe, eliminating an estimated 90 to 96% of all marine species and approximately 70% of terrestrial vertebrate species, and fundamentally reshaping the composition of ecosystems for the subsequent Mesozoic era. The causes of this extinction appear linked to massive volcanic eruptions in what is now Siberia, the Siberian Traps, which released enormous quantities of carbon dioxide and other gases over a geologically brief interval, triggering severe global warming, ocean acidification, ocean anoxia, and ozone depletion. The end Cretaceous extinction 66 million years ago, though less severe in terms of species loss, eliminated the non-avian dinosaurs and numerous marine groups including ammonites and marine reptiles, and has been definitively linked to the impact of an approximately 10-kilometre asteroid in what is now the Yucatan Peninsula of Mexico, with the crater at Chicxulub representing the impact site. This impact released energy equivalent to roughly 100 million megatons of TNT, producing global wildfires, a years-long impact winter due to debris blocking sunlight, and severe acid rain, with the combined environmental effects devastating both terrestrial and marine ecosystems. The evolution of intelligence and technology in the lineage leading to modern humans represents a recent development in cosmic terms, with the genus Homo arising approximately 2 to 3 million years ago in Africa, and the species Homo sapiens appearing approximately 300,000 years ago. The development of stone tool technology, controlled use of fire, language, symbolic thought, and complex social organisation proceeded through stages whose details remain subject to revision as new fossil and archaeological discoveries accumulate. The dispersal of modern humans from Africa into other continents occurred in multiple waves, with the most significant expansion beginning approximately 60 to 70,000 years ago and reaching Australia by perhaps 50,000 years ago, Europe by approximately 45,000 years ago, and the Americas by at least 15,000 years ago and possibly earlier. This expansion brought modern humans into contact, and sometimes competition with other hominin species, including Neanderthals in Europe and Western Asia, and Denisovans in Eastern Asia, with genetic evidence demonstrating interbreeding between these groups that has left traces in the genomes of present-day non-African populations. The development of agriculture beginning approximately 10 to 12,000 years ago in multiple independent centres including the Fertile Crescent, China, Mesoamerica, and elsewhere, fundamentally transformed human societies, enabling population growth, sedentary settlement, social stratification, and eventually the development of writing, cities and states that characterize complex civilizations. The scientific study of the universe beyond Earth relies on techniques for observing electromagnetic radiation across the full spectrum, from radio waves through infrared, visible light, ultraviolet, X-rays and gamma rays, as well as on detection of particles including cosmic rays and neutrinos, and most recently on detection of gravitational waves. Each of these observational channels provides information about different physical processes and conditions, with radio observations revealing cool gas and energetic electrons in magnetic fields, infrared observations penetrating dust that obscures visible light and revealing thermal emission from warm objects, visible light observations providing the most familiar views of stars and galaxies, ultraviolet observations probing hot stellar atmospheres and active galactic nuclei, X-ray observations detecting million-degree gas in galaxy clusters and around black holes, and gamma-ray observations sampling the most energetic phenomena in the universe. Neutrino astronomy, though limited by the extreme difficulty of detecting these weakly interacting particles, has successfully observed neutrinos from the Sun, from supernova 1987A in the Large Magellanic Cloud, and from various high-energy astrophysical sources detected by the IceCube Observatory at the South Pole. Gravitational wave astronomy, inaugurated by the first direct detection in 2015, has opened a fundamentally new window on the universe, providing information about sources including binary black hole mergers, binary neutron star mergers, and potentially other phenomena invisible to electromagnetic observations. The expansion of observational capabilities has revealed cosmic phenomena whose existence would have seemed impossible to earlier generations of astronomers. Black holes, predicted theoretically from general relativity, but long considered potentially mere mathematical curiosities, have been established as physical realities through observations of stellar motions around the 4 million solar mass black hole at the centre of the Milky Way, through gravitational wave detections of merging black hole binaries, and through direct imaging of the shadows cast by supermassive black holes against the surrounding emission by the Event Horizon Telescope. Pulsars, rapidly rotating neutron stars emitting beamed radio emission, were discovered in 1967 and initially generated speculation about possible artificial origin, before being recognised as natural objects, their precise timing now employed as probes of gravitational waves, tests of general relativity, and laboratories for physics under conditions unattainable on Earth. Gamma-ray bursts, brief but extraordinarily intense flashes of high-energy radiation, were first detected by military satellites in the 1960s, and their origin remained mysterious for decades before being established as arising from either the collapse of massive stars or the merger of compact objects at cosmological distances. Fast radio bursts, first recognised in 2007, remain not fully explained despite the recent association of at least some with magnetars, highly magnetised neutron stars producing sporadic energetic outbursts. The search for life beyond Earth has progressed from philosophical speculation to active scientific investigation, employing both in situ exploration of solar system bodies and remote observation of planets orbiting other stars. Within the solar system, Mars has received the most sustained attention as a possible abode for past or present life, with evidence for ancient water flow, the detection of seasonal methane variations whose origin remains debated, and ongoing rover investigations of geological and chemical conditions. The subsurface oceans now known to exist beneath the icy surfaces of Europa, Enceladus, and possibly other outer solar system moons present environments potentially hospitable to life, shielded from radiation and supplied with chemical energy through interactions between water and rock. The detection of phosphine in the atmosphere of Venus, announced in 2020, generated considerable excitement as a possible biosignature, before subsequent analyses raised questions about both the detection itself and the biological interpretation, illustrating the difficulties inherent in remotely identifying signs of life. The icy plumes erupting from Enceladus, sampled by the Cassini spacecraft, contain organic molecules and molecular hydrogen consistent with hydrothermal activity on the seafloor, making this small Saturnian moon a high-priority target for future astrobiological investigation. The discovery of planets orbiting stars other than the Sun has transformed understanding of planetary systems from a single example to a statistical sample, now numbering over 5,000 confirmed planets, with thousands more awaiting verification. The first exoplanet orbiting a Sun-like star, 51 Pegasi b, was detected in '95 through the radial velocity method, which identifies the wobble induced in a star by an orbiting planet, and this discovery revealed an unexpected configuration with a Jupiter-mass planet orbiting extremely close to its host star with a period of only about 4 days. Such hot Jupiters, absent from our own solar system, demonstrated that planetary architectures could differ substantially from the familiar arrangement and prompted revision of theories of planet formation and migration. The Kepler Space Telescope, operating from 2009 to 2018, revolutionized the field through transit photometry, detecting planets by the minute dimming they cause when passing in front of their host stars, and its observations revealed that small planets between the sizes of Earth and Neptune are extremely common, that multi-planet systems are typical rather than exceptional, and that planets exist in configurations ranging from tightly packed to widely spaced. The TRAPPIST-1 system, containing 7 approximately Earth-sized planets orbiting an ultra-cool dwarf star, includes several planets in the habitable zone where liquid water might exist on the surface, and represents a particularly interesting target for atmospheric characterization with the James Webb Space Telescope. The search for biosignatures in exoplanet atmospheres focuses on gases that might indicate biological activity, including oxygen, ozone, methane, nitrous oxide, and various other species whose simultaneous presence might be difficult to explain through abiotic chemistry alone. The challenge lies in distinguishing biological from geological or photochemical sources, in accounting for the wide range of possible atmospheric compositions and planetary conditions, and in recognizing that alien biochemistry might produce signatures quite different from those expected based on terrestrial biology. The detection of atmospheric constituents through transmission spectroscopy, which observes starlight filtering through a planet's atmosphere during transit, or through emission spectroscopy, which directly samples planetary light, requires extremely precise measurements and careful modelling to extract the weak planetary signals from the much brighter stellar contribution. Early results from the James Webb Space Telescope have begun characterising exoplanet atmospheres with unprecedented detail, detecting carbon dioxide, water, and other molecules in the atmospheres of gas giant exoplanets, with observations of smaller rocky planets expected to follow as techniques and observation times accumulate. The Drake equation, formulated in 1961 as a framework for estimating the number of technologically communicative civilizations in the galaxy, multiplies together factors representing the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the probability of life arising, the probability of intelligence evolving, the probability of technology developing, and the lifetime of technological civilizations. While the early terms in this sequence have become increasingly constrained by observations, with billions of potentially habitable planets now estimated to exist in the Milky Way alone, the later terms remain essentially unconstrained by empirical data, with estimates of the probability of life originating or intelligence evolving spanning many orders of magnitude depending on the assumptions employed. The Fermi paradox, often summarized as "where is everybody?", poses the apparent contradiction between the high probability estimates for extraterrestrial intelligence and the lack of any confirmed evidence for its existence, a tension that has generated numerous proposed resolutions, including the possibilities that intelligent life is rare, that technological civilizations are short-lived, that interstellar travel is impractical, that extraterrestrial civilizations exist but choose not to communicate or visit, or that evidence exists but has not been recognized as such. The future of the universe, extending far beyond the timescales relevant to human concerns, can be projected through extrapolation of known physical processes, though the reliability of such projections decreases with the temporal distance involved. The Sun will exhaust the hydrogen fuel in its core in approximately 5 billion years, expanding into a red giant that may engulf Earth's orbit before shedding its outer layers as a planetary nebula and leaving behind a white dwarf that will slowly cool over trillions of years. The Milky Way and Andromeda galaxies will merge in approximately 4.5 billion years, producing gravitational disruption of stellar orbits, though not direct stellar collisions, eventually forming an elliptical galaxy, sometimes nicknamed Milkomeda. On longer timescales, if current understanding is correct and dark energy continues to drive accelerating expansion, increasingly distant regions of the universe will pass beyond the cosmic horizon, becoming causally disconnected and unobservable, with the observable universe eventually shrinking to encompass only the local gravitationally bound group. Star formation will cease as the supply of gas is consumed or dispersed. Existing stars will progressively exhaust their fuel and cool, and on timescales of trillions to perhaps a Google years, even the compact remnants will decay through quantum processes, leaving an increasingly dilute sea of particles and radiation asymptotically approaching but never quite reaching thermal equilibrium. This trajectory represents only one possible future among several permitted by current understanding, with alternatives depending on properties of dark energy that remain uncertain. If dark energy proves to be a cosmological constant as current evidence suggests, the scenario outlined above represents the probable long-term fate. If dark energy density increases over time, a possibility termed phantom dark energy, the expansion could accelerate to the point of tearing apart galaxies, stars, planets, atoms, and eventually space-time itself in a big rip singularity occurring at a finite time in the future. If dark energy density decreases and eventually reverses sign, the expansion could decelerate, halt, and reverse, producing a contracting phase that would ultimately end in a big crunch singularity, the time reverse of the Big Bang. Each of these scenarios and others remain possible within the constraints imposed by current observations, and distinguishing among them will require more precise measurements of the equation of state of dark energy over cosmic history. The intellectual history through which this understanding of the universe has developed spans only about 4 centuries of serious scientific investigation, a period during which conceptual frameworks have been repeatedly overturned and replaced by more comprehensive successors. The Ptolemaic geocentric cosmos, which placed Earth at the centre of a universe consisting of nested crystalline spheres carrying the celestial bodies, dominated European thought for over a millennium before giving way to the Copernican heliocentric model, in which Earth became merely one of several planets orbiting the Sun. The Newtonian synthesis of the 17th century established a universal mechanics applicable to both terrestrial and celestial phenomena, replacing the Aristotelian distinction between corrupt earthly matter and perfect heavenly substances with a single set of laws governing all material bodies. The discovery in the 19th century that stars are suns at vast distances, some similar to our own and others vastly different, expanded the cosmic inventory beyond what had previously been imagined. The recognition in the early 20th century that nebulae are external galaxies comparable to the Milky Way, that the universe is expanding from a hot dense origin, and that gravity curves space and slows time, represented conceptual revolutions whose implications continue to be worked out. Each of these transitions involved not merely the addition of new facts, but the fundamental revision of categories and assumptions that had structured previous understanding. The relationship between theoretical prediction and observational discovery has varied across different episodes in this history, with some phenomena predicted before observation and others discovered unexpectedly. General relativity predicted gravitational waves in 1916, but their detection required a century of technological development. The cosmic microwave background was predicted as a consequence of Big Bang cosmology before its accidental discovery confirmed the theory. Pulsars and gamma-ray bursts were discovered without theoretical anticipation, their explanation following rather than preceding observation. The accelerating expansion of the universe, revealed by supernova observations in 1998, was genuinely unexpected, contradicting the theoretical expectation that expansion should be decelerating under gravitational attraction. This interplay between theory and observation, each informing and constraining the other, represents a methodological ideal whose concrete realization differs substantially across different domains and historical periods. The instruments employed in astronomical observation have evolved from naked eye viewing through optical telescopes of progressively increasing aperture to arrays of specialized detectors spanning the electromagnetic spectrum and beyond. The limitations imposed at each stage by available technology have shaped the questions that could be addressed and the phenomena that could be perceived, with each extension of capability revealing features invisible to previous generations. The invention of the telescope in the early 17th century revealed the phases of Venus, the moons of Jupiter, and the resolution of the Milky Way into individual stars, observations that contributed to the abandonment of geocentrism. The development of spectroscopy in the 19th century enabled determination of the chemical composition, temperature, velocity, and other properties of celestial objects from analysis of their light, transforming astronomy from a purely positional to a physical science. The extension of observations beyond the visible spectrum, beginning with the discovery of infrared radiation in 1800 and expanding throughout the 20th century, revealed cosmic phenomena in visible light, including the cosmic microwave background, X-ray binaries, and gamma-ray bursts. The development of electronic detectors replacing photographic plates dramatically increased sensitivity and enabled digital processing of astronomical data. The placement of telescopes in space above the obscuring and distorting effects of Earth's atmosphere provided access to wavelength ranges blocked by atmospheric absorption and achieved angular resolution limited only by diffraction rather than atmospheric turbulence. The computational resources available for analysing astronomical data and simulating cosmic processes have grown by many orders of magnitude over the past half-century, enabling investigations impossible with earlier technology. Numerical simulations of cosmic structure formation now track the gravitational evolution of billions of particles representing dark matter, including the hydrodynamics of gas, the formation and evolution of stars, the effects of supernova and black hole feedback, and the observable properties of the resulting galaxies, producing synthetic universes whose statistical properties can be compared with observations. Machine learning techniques increasingly assist in classifying objects, identifying anomalies, and extracting patterns from datasets too large for human inspection. The exponential growth in data volume from surveys scanning ever larger areas of sky to ever greater depths creates both opportunities for new discoveries and challenges for data management and analysis. The collaborative organization of astronomical research has correspondingly evolved from individual observers using personally constructed instruments to large international collaborations operating shared facilities and producing data products available to the entire research community. The philosophical implications of cosmological knowledge extend beyond purely technical concerns to questions of human significance, meaning, and identity that have occupied thinkers across cultures and centuries. The displacement of Earth from the cosmic centre, the recognition of the solar system as an ordinary stellar system in an ordinary galaxy in an ordinary supercluster, and the measurement of cosmic timescales against which human history represents an infinitesimal fraction, have challenged anthropocentric conceptions of the cosmos and stimulated reflection on what meaning or purpose might attach to human existence in an apparently indifferent universe. The possible existence of life elsewhere in the cosmos, whether demonstrated or merely inferred as probable, would further contextualize the human situation, perhaps revealing terrestrial life as one instance of a common cosmic phenomenon, or alternatively as an isolated peculiarity, each possibility carrying different implications for self-understanding. The ultimate fate of the universe, whether in heat death, big rip, big crunch, or some other scenario, confronts attempts to locate enduring significance in cosmic processes that appear to terminate in equilibrium, dissolution, or singularity. These implications have generated varied responses across philosophical, religious, and literary traditions, ranging from despair at cosmic insignificance to celebration of the universe's creative potentiality to indifference toward questions deemed beyond practical concern. The uncertainty inherent in current cosmological understanding deserves emphasis as a counterweight to any impression of completeness or finality that summary accounts might inadvertently convey. The nature of dark matter and dark energy, constituting together some 95% of the cosmic mass energy content, remains essentially unknown despite decades of investigation. The initial conditions of the universe, the reason for the particular values of fundamental constants, and the cause or nature of the cosmic expansion itself lie beyond the explanatory reach of current theories. The possibility that the observable universe represents only a small and perhaps unrepresentative portion of a larger multiverse, whether conceived as a collection of causally disconnected regions with different physical properties or as a quantum superposition of alternative histories, raises questions about the appropriate scope of cosmological explanation and the meaning of scientific explanation itself when evidence for proposed entities may be in principle inaccessible. The history of cosmology provides ample precedent for conceptual revolutions that rendered previously accepted frameworks obsolete, and there is no principled reason to assume that current understanding has achieved immunity from similar revision. The relationship between cosmology and other domains of human knowledge involves both methodological borrowing and conceptual tension. The application of physics to cosmic scales assumes the universality of physical laws, an assumption supported by observations of identical spectral lines in distant galaxies, and by the coherence of cosmological models, but ultimately grounded in philosophical conviction rather than strict proof. The intersection of cosmology with philosophy of science generates debates about the scientific status of claims concerning unobservable entities, unique events, and regions beyond causal contact. The historical dimension of cosmology, concerned with reconstructing past states of a system that cannot be directly observed, shares methodological characteristics with historical sciences including geology and evolutionary biology, each facing challenges in establishing causation and testing hypotheses about unrepeatable events. The popular reception of cosmological ideas has been shaped by cultural contexts and interests that extend far beyond technical concerns, with the Big Bang in particular generating associations with creation narratives that scientific cosmology neither requires nor excludes but cannot directly address. The technology and instrumentation employed in contemporary cosmological research represent substantial investments of resources, expertise, and international coordination, reflecting judgments about the value of cosmological knowledge and the priority it deserves relative to competing claims on scientific effort. The James Webb Space Telescope, launched in 2021 after decades of development at a cost of approximately $10 billion, represents the most powerful astronomical instrument yet deployed in space, capable of detecting infrared radiation from the earliest galaxies, characterizing exoplanet atmospheres, and observing cosmic processes at wavelengths and sensitivities inaccessible to previous facilities. Ground-based facilities including the extremely large telescope under construction in Chile, with a primary mirror 39 meters in diameter, and the Vera C. Rubin Observatory with its wide-field survey capability, will complement space observations with capabilities optimized for different science goals. The development of next-generation gravitational wave detectors including space-based observatories, such as the proposed LISA mission, will extend sensitivity to lower frequencies corresponding to supermassive black hole mergers and potentially to the gravitational wave background from the early universe. These projects embody accumulated technical knowledge spanning optics, materials science, cryogenics, detector physics, data processing, and numerous other specialized domains, their success depending on the coordinated contributions of thousands of individuals across many institutions and nations. The transmission of cosmological knowledge to broader publics involves interpretive choices about emphasis, metaphor, and simplification that inevitably shape reception and understanding. The metaphor of the expanding balloon with dots representing galaxies, commonly used to convey the expansion of space, captures certain features while potentially misleading about others, particularly regarding the question of what space expands into. Visualizations of cosmic structure, necessarily representing three-dimensional distributions on two-dimensional media, and often employing false color to distinguish features, shape intuitions in ways that may not correspond to the actual experience of observation. The narrative framing of cosmological discoveries in terms of human interest, competitive priority, and dramatic breakthrough, while serving communicative purposes, may obscure the collective and cumulative nature of scientific progress and the uncertainties that typically accompany initial reports. The responsibility for accurate communication rests not solely on popularizers, but also on working scientists whose claims filter through multiple stages of interpretation before reaching general audiences, each stage introducing potential distortions. The question of what further discoveries await regarding the nature and history of the universe cannot be answered with confidence, since the most significant advances have often come from directions not anticipated in advance. The detection of gravitational waves, long sought, but achieved only through technological advances unforeseeable decades earlier, illustrates how instrumental capability can suddenly unlock phenomena previously beyond reach. The discovery of the accelerating expansion, emerging from observations undertaken for quite different purposes, demonstrates how attention to anomalous results can reveal unexpected features of reality. Future surveys of unprecedented scope and sensitivity, next-generation particle physics experiments, novel detection techniques, and theoretical breakthroughs not yet conceived may together reshape understanding in ways that make current knowledge appear as limited in hindsight as earlier conceptions now appear from the present perspective. The universe continues to present itself for investigation, its properties fixed regardless of human inquiry, but progressively revealed through the sustained effort of observation, analysis, and interpretation that constitutes the scientific enterprise.